Okay, just testing everything out. Alright, we're live on YouTube. X will play catch up for another 10 minutes. Twitch is not doing great. Oh, there we go. Twitch is there. Right, sound check done. Happy go lucky, all that stuff, very nice. So we'll just wait for Twitter to play catch up in the next 10 minutes because it doesn't ever seem to start before it's actually like ready. Like until you schedule the scheduled time, so just wait until for it to finish and then we'll get on it. What up, people? How you doing tonight? Try to switch from C++ to Python. Why is that? Get started soon, folks. 5 minutes just waiting for Twitter to play catch up. Alright, Twitter should be caught up now. Let me see. Almost. I think it's got like a minute left. Right. Looks like Twitter is now live, so we will crack on. Okay. So hopefully this is the last night of data structures and algorithms. Oh wait, no, I think. There we go. We're back. Cool. So this would hopefully be the last night of this. We're on the last two chapters of data structures and algorithms, and it's BFS, DFS, and MP. Breadth first search, depth first search, and then I don't know the last two, to be fair. Hey peeps, how's it going? So we're going to start off. So breadth first search. Now I've never done like algorithms like a lot before, so this is like me rinsing through like the whole module, getting scripts with it and stuff. So I'm curious as to breadth first search is. And so I roughly conceptually know what it is, but I don't know what it is in practice. So breadth first search is an algorithm for traversing or searching tree or graph data structures. It starts at a root, some arbitrary node in a graph, and explores all the neighbor nodes at the present depth before going on to the nodes at the next level. So let's have a listen to the video Lane has kindly given us. These are great videos, the way he makes these.
Breadth first search, or BFS for short, is one of those graph traversal algorithms that you're just going to encounter time and time again as a developer. Picture this. You're at a party. Unlikely, I know. But you want to spread some juicy gossip. You're not a monster. You want to do it efficiently. That's really what breadth first search does. It spreads out across a graph in a fairly efficient manner. And it does so by going wide instead of deep. Let me show you what I mean. Let's pretend we have this graph. Now, BFS has to start somewhere. Let's just choose to start at A. So we'll add A to our to-visit list, and then we'll actually visit it. When we visit it, we cross it off, and we add its neighbors to our to-visit list. In this case, B and E. Next, we actually visit B, cross it off, and add its neighbors, C and F, to our to-visit list. Then we go back to the next, or I should say the first uncrossed off node on our list, E. We visit it, cross it off, and add its neighbors to our to-visit list. We can ignore F because it's already on our list. Next, we visit C and add D and G. Then we visit F and add J. We visit I and add L. Then we visit D, which adds actually no new neighbors to our list. We visit G, which adds H and K. Next, we visit J, L, H, and K, none of which add new neighbors to our to-visit list, which means we've traversed the whole graph. Now, breadth first search has a time complexity of order V plus E, which is kind of weird. You might not be used to seeing big O in terms of V and E. You're probably used to N. But V just stands for vertices, right, or nodes in the graph, in this case, all the letters. And then E stands for the edges, the connections between the nodes in the graph. So in the worst case, E can get quite large if every vertice is connected to every other vertice, which effectively makes it order V squared. But again, that's only if every node is connected to every other node. So when might you use BFS? Well, sometimes it's used to find the shortest path in a graph, and it's often used for things like web crawling, where you probably want to start at something like a home page, which is probably very, very likely trafficked by lots of people, and then you want to go breadth first through the site, right? Going to every interlinking page on the site, but down from the root where things are most authoritative. In other words, you don't want to dig all the way down to some obscure blog article first. No, you want to go through all of the most highly ranking pages on the site first. So web crawlers are a very common use case for breadth first search. Kind of as a rule of thumb, breadth first search is really good if the solution you're for, or the nodes you're looking for in a graph, tend to be really close to your starting point. And that doesn't always mean it's the best choice. Depth first search, which is kind of the inverse of breadth first search, is really good when you think that the solution is far away. Maybe you're making your way through a maze. Depth first search also doesn't require as much memory as breadth first search, because it doesn't need to keep track of this giant to-visit list. It's a less stateful algorithm. But that's a story for another video.
Like, that's gonna happen.
Good video, Lane. I like it. Good explanation of it. So, stable sorting. So non-integer sets are not stable in Python. The order of the elements in a set is not guaranteed to be the same each time you iterate over it. While testing, we want our algorithm to search the same way every time to make debugging easier. Python offers a sorted function we can call on our set that will return a sorted iterable. So sorted items, sorted and the unsorted set. Okay, so the assignment. So graphs are useful at locked in for more than just representing social connections. We'll also use it to build our geographic search feature. We have a graph of cities where each city is a vertex and each road connecting to cities is an edge. Complete the breadth first search method on the graph class. So this method traverses a graph level by starting from a specified vertex and returns all vertices in the order they were visited. The breadth first approach ensures we explore all vertices at the current distance from the start before moving further away. So initialize tracking structures. So create a list to track visited vertices. So visited vertices equals just an array. Create a list to use as a queue for vertices waiting to be explored. So vertices to be explored. So vertices to be explored. Begin the search. So add the starting vertex to the queue. Oh, 1 minute. Important thing of the day. Okie dokie. Important job of the day done. Right, so we've got so add the starting vertex to the queue. So it's going to be vertices to be explored dot append v. I'm guessing is the vertex. So I'm pretty sure that's done. Process the queue until empty. All right. Remove the first vertex from the queue and add it to the visited list. What? Add the starting vertex to the queue. Remove the first vertex from the queue and add it to the visited list. So for remove the first vertex from the queue. So append vertex. And then can I just like do? I can't remember how you delete like from a list. Can you just do like delete? Delete list deletion. Yeah. Yeah, delete like that. So delete vertices to be explored. Vertex. Get a sorted list of this vertex's neighbors. The only problem with that is I don't know what a get the vertex's neighbors. For each neighbor, if it is neither visited nor queued, add it to the queue. I don't know what the what wait, let me just print this out so I can see what it is. So like what is in vertex? List indices must be integers or slices, not strings. Create a list to track visited vertices. Create a list to use as a queue for vertices waiting to be explored. So they're both empty to start with. Add the starting vertex to the queue. I guess I just do that, right? Doesn't like that for some reason. New York. List indices must be integers or slices, not strings. Why? That doesn't make any sense. List strings. List indices must be integers or slices, not string. Let's print something here. You just get there. Oh, an index, right? Silly me. Okay, so we can do index. Can we do it like that? Hold on. Python for loop index. Enumerate. Right. What's this do? Change the enumerate object. Iterable must be a sequence. Iterate. Okay. Oh, then put it into a list. It's a bit weird. Okay. Get a sorted list of the vertex's neighbors. Remove the first vertex from the queue and add it to the visit. So process the queue until empty. So remove the first vertex from the queue and add it to the visited list. Get a sorted list of the vertex's neighbors. For each neighbor, when complete, return the visited list contain vertices in the order they were discovered. neither is visited or queued, add it to the queue. So for hold on. Spell it properly. Neighbor in so if neighbor is not in yeah. I mean, I feel like this should be simple, right? I'm making it a little bit too complicated. At least that's what it feels like. So create a list to track the visited vertices. Yep, done that. Do I have to? Oh, I might have to use the self class. Hold on. Create a list as you use the queue vertices waiting to be explored. Add the sign vertex to the queue. Yeah, done that. Process queue semantics. So remove the first vertex from the queue and add it to the visited list. Process the queue until empty. Yeah. Yeah, I'm pretty sure that's fine. Get a sorted list of this vertex's neighbors, or if it doesn't have neighbors. So for each neighbor, So here it's going to be index vertex. Okay. So that point, it's empty. So get a sorted list of this vertex's neighbors. But how do I know what the neighbors are? I have to refer to the self graph, the graph. Self.graph. Get sorted list. Okay. So I guess self.graph. And then give it the vertex. Is that right? So it's not quite sorted. Oh no, it is. So get a sorted list of the vertex neighbors for each neighbor. If it is neither visited nor queued, add it to the queue. Add, and then neighbor. Okay. Python delete from list. Oh, while iterating. Work. Vertices to be explored. Yeah, so it's adding. Yeah, it works. Okay, so it's moving as I expected. Okay. I think I might have got this part wrong, so figuring out which are the neighbours. So visiting, expecting, visiting, expecting, fail. It is neither visited. So the first would be Cairo, London, Tokyo. So visiting, expecting, visiting London. Why would London be next? I'm not really sure. I think I got this part wrong, but I'm not sure why. I think because I'm just sort of like referencing the children of it. We're meant to like the self-dot graph again. Neighbor vertexes neighbors. But how do you know? You get all the neighbors or just like the ones to the left and right? That's the part I'm stuck at. I'm gonna ask Boots for help on this and stuff. I think I'm close, Boots, but I need your help. Go on then. Yep. Yeah, I can see you're working on the breadth first search algorithm. You're definitely on the right track with your approach, but there are a couple of issues that are causing the algorithm to behave incorrectly. Looking at your output, I notice London appears twice in your visited list, and the order isn't quite what's expected. This suggests there might be an issue with how you're managing the queue and checking for already visited or queued vertices. Let me ask you a few questions to help you debug this. So, queue management. In a typical breadth first search, we use a queue, first in, first out, using a for loop to iterate over the vertices to be explored, but you're also modifying this list during the iteration. What do you think might happen when you remove an item from a list while iterating over it? I guess it's going to skip, isn't it? That's a good point. Neighbor checking. Look at the condition if neighbor not in visited vertices or that. Think about this logic. When do you want to add a neighbor to the queue? Should it be when the neighbor is not visited and not in the queue? Can you think through these two issues and see what adjustments might help? So vertices to be explored. Waiting to be explored. Begin the search. Add the starting vertex around. Process the queue until empty. So remove the first index from the queue and add it to the visited list. Yeah, create a list to track visited vertices and create a list to use as a queue for vertices waiting to be explored. Process the queue until empty. Would a while loop be better suit? I think 4 is fine, but basically need two different things to leap over, don't we? So, oops. So maybe we don't need to do that. Is that it? Why did the instructions tell me to remove it from the queue then? Let's have a look at that solution. Visited to visit, append, pop. To visit was popped. With seeks to be explored. So why did appended? while to visit. Okay, so they use a while loop, but still did the same sort of like mutation thing. Okay, so it's pretty much the same. Excellent question. You've actually discovered something interesting about different ways to implement breadth first search. While the instruction is meant to removing from the queue because the traditional breadth first search algorithm uses a while loop with explicit queue operations like remove from the front of the queue, visited, append, yeah. However, your approach is actually quite clever. You're using a for loop that dynamically extends the list as you iterate. This works because Python's for loop automatically handles the growing list. When you append new vertices to be explored, the loop will eventually reach them. Your solution is more concise, no need for explicit queue management. Still correct, produces the right breadth first search traversal order, avoids the potential issues with modifying a list while iterating, since you're only appending, not removing during iteration. The key insight you had was changing from or to and in your neighbor check. That was a crucial fix. You correctly identified that you only want to add a neighbor if neither visited. Yeah, okay. So it's a little bit syntactical thing I didn't really kind of get there, but I got it now. So complete graph. A complete graph is a graph where every pair. Hold on. Complete graph. A complete graph is a graph where every pair of vertices is connected by an edge. Okay, so the formula for the number of edges in a complete graph is n times n minus 1 divided by 2, where n is the number of vertices. How many edges will a complete graph with 6 vertices have? Okay. So 6 times 6 minus 1, so 6 times 5 is 30, divided by 2 is 15. A complete graph must have more vertices than edges, more edges than vertices, edges connecting each pair of vertices, that one, edges connecting each pair of vertices. Depth first search, okay. So depth first search, DFS, is just another algorithm to traverse a graph. Kind of like breadth first search, it starts at root node, some arbitrary node on the graph, and explores as far as possible along each branch before backtracking and starting down the next branch. Okay. I'll pass it down each branch before backtracking and starting the next branch. The provided image depicting depth first search is illustrative and not directly related to specific code assignment in this lesson. That's fine. Okay. Confused as heck to look at. 1, 2, 3, 4, 5, 6. Okay, going that way, and then 7, 8. All right, just kind of demonstrating which way it goes. Okay, so the locked-in executives want us to add. Whoops, I don't need to go to the shop. The locked-in executives want us to add a depth-first search feature to geographic search. Complete the depth first search and depth first search R methods. The depth first search R method is a recursive helper method with depth first search. Complete the depth first search function. It takes a start vertex as input. It takes a start vertex as input and traverses the graph in a depth first manner and record the vertices it visits in a list and returns it. It should create an empty list to store the visited vertices. So visited vertices equals empty list. Called depth first search R with the empty list and the start vertex. Okay, so self dot. Visited vertices and start vertex. Return the list of the visited vertices after depth first search has filled it in. Okay, so return visited vertices. Pretty sure that's straightforward. So complete the depth first search R function. It takes a list of vertices that have been visited so far and the current vertex is input. It should visit the current vertex by Visit the current vertex by adding it to the list. Hold on. It takes a list of vertices that have been visited so far, and a current vertex is input. Visit the current vertex by adding it to the list. So I guess visited dot append current vertex. Okay, sorted list of the neighbors of the current vertex. So neighbors sorted list. So self.graph and then current vertex like we did before. For each of those neighbors. So for if the neighboring vertex hasn't been visited yet, visit it by recursively calling with the neighboring vertex. Okay, so if neighbor not in visited, then self dot depth first search are visited. Is that the first part? Yeah, visited, and then the neighbor. Okay, that was a lot simpler. Is that pretty simple? So depth first search versus breadth first search. You should use depth first. Should you use depth first search or breadth first search when traversing a graph? Well, it depends. Let's look at some rules of thumb we can use to help make the decision. Is the solution close to the root? If you have good reason to believe the vertex you're looking for is close to the root, where you plan to start searching, then breadth first search should be faster. Does the graph have wide levels? Imagine a tree-like graph with 10 vertices on the first level. Each of those 10 vertices point to another 10 vertices. The number of vertices at each level will be 1, 10, 100, 1,000, 10,000. Because breadth first search stores each horizontal level in memory at the same time, you might run out of memory. Depth first search would likely be more memory efficient. Is the search space infinite? In some searches, the graph has infinite size. For example, imagine a simulation of a game of chess. The first level of the graph represents all the possible current moves. The next level, all the possible second moves, and this goes on forever, especially when you consider that there are possible loops within the game, moving a queen back and forth. In these cases, true depth first search is practically impossible. You would either be forced to use breadth first search, use another algorithm, put a limit on how far your depth first search algorithm can search before returning. Which search strategy would you prefer if the solution is likely very shallow in a tree-based graph? So breadth first search. Which search strategy would you prefer in a search space with infinite depth? Breadth first search. Which search strategy would use less memory in a wide graph? Depth first search. Okay. Breeze that one. And it's only 20 past 8. But hella heck, we got 20 lessons on this one on MP and MP and whatever else it is. PM. MP and wherever it is. So MP, so non-deterministic polynomial time, MP, is the set of problems whose solutions can be verified in polynomial time, but not necessarily solved in polynomial time. P is in MP, because all problems that can be solved in polynomial time can also be verified in polynomial time. All the problems in P are also in MP. Hold on. Non-deterministic complexity. Okay? In computational complexity theory, non-deterministic polynomial time is a complexity class used to classified decision problems. NPs are set of decision problems for which the problem instances where the answer is yes have proofs verified. Okay, crikey. Non-deterministic is a set of problems whose solutions can be verified in polynomial time, but necessarily solved in polynomial time. P is in MP because all problems that can be solved in polynomial time can also be verified in polynomial time. All the problems in P are also in MP. So the oracle. A good way of thinking about problems in MP is to imagine that we have a magic oracle that gives us potential solutions to problems. So imagine we have a magic oracle that gives us potential solutions to problems. Here would be our process for finding if a problem is in MP. What's polynomial time? Hold on. Polynomial time. An algorithm is said to be a polynomial time if its running time is upper bounded by a polynomial expression in the size of the input for the algorithm that is. Oh my gosh. Explain it like I'm 5, please. Well, let's try that. Croc, come on. Save some skin. Can you explain polynomial time and non-deterministic polynomial time? Why not? Let's try with the expert mode. Because I'm reading this and I'm like, whoa. A good way to think about problems in MP is to imagine that we have a magic oracle that gives us potential solutions to problems. Here would be our process for finding if a problem is MP. Present the problem to the magic oracle. The magic oracle gives us a potential solution. We verify in polynomial time that the solution is correct. If we could do the verification in polynomial time, the problem is in MP, otherwise it isn't. Okay. Polynomial time, solving easy puzzles. Like solving easy puzzles. So imagine you have a puzzle with a few pieces, like 10 pieces. You can put it together pretty quick, right? Now what if the puzzle is 100 pieces? It takes longer, but not crazy longer. Maybe just a few times more. Like if it took 1 minute for 10 pieces, it might take 10 minutes for 100. That's like polynomial time. It's a fancy way grown-ups say a problem is solvable in a reasonable amount of time, even if the puzzle gets bigger. Computers love these because they can finish fast without getting too tired. Non-deterministic polynomial time, like guessing the right answer. Now think of a harder game. You have a huge maze and you need to find the way out. If you try every path one by one, it could take forever. But what if you could magically guess the right path super quick and then just check if it's correct in a short time? That's like non-deterministic polynomial time. We call it MP for short. The non-deterministic part means the computer gets to guess, like having a magic helper, and the polynomial time part means checking the guess doesn't take too long. Some puzzles are easy to check but hard to solve without guessing. Like knowing if a key fits a lock is fast, but finding the right key from a million is tough. In real life, we don't have magic guesses, so some MP problems make computers work really hard. Scientists wonder if all these guessing games can be turned into easy puzzles without magic. That's a big mystery called P versus MP. Okay, let's listen then.
Question of P versus NP. Probably the favorite problem of every computer scientist. Now, I hate acronyms, so let's break down what P and NP actually stand for. P stands for polynomial time. It's just a classification of algorithms that are fast enough. NP stands for non-deterministic polynomial time, which is a very confusing term, but what it really means is a lot simpler. To quote from the Introduction to the Theory of Computation, a book, it says, NP is the class of algorithms that has polynomial time verifiers. Now, the whole bit about non-determinism, there is like a technical reason for why that terminology is used, but the important thing to understand is that algorithms in complexity class NP their solutions can be verified in polynomial time. And we'll get to what exactly that means in just a second. So first, just what is polynomial time? Well, let's take a look at all of our different big O classifications. We've got order 1, constant time. We've got order log n, logarithmic time, order n, linear time, order n squared, order n cubed. And then after order n squared and n cubed, we kind of hit a wall where all the algorithms go from being practical. Like, n squared and n cubed are slow, but they're not that slow. Like, you can still run these algorithms and get reasonable results. You kind of hit a wall where order 2 to the n and order n factorial, these algorithms grow in slowness at an exponential rate. They get so slow so quickly that even for small input sizes, for small numbers of n, they become impractical. Like, you run this on modern hardware and it's just never going to stop. Your computer will be frozen for the rest of your life. And that's where we draw the line between the polynomial time algorithms and the exponential time algorithms. So for an algorithm to be in complexity class P, it just needs to be in one of these. We just kind of lump them all together and say, this is polynomial time. These algorithms are practical. All these other ones, they're too slow. They're exponential. Okay, so what's this bit about NP and verification? Let's just imagine that we have a problem where there's 10 different cities on a graph. And our job is to find the path through all 10 cities, if one exists, that is less than 100 miles in total. Well, the algorithm for finding out whether one of these paths exists or not is actually n factorial. We have to check every single combination of paths through all 10 cities. And the number of paths to check is n factorial, which is a massive number. I mean, just 10 factorial is already over 3 million. So this algorithm is not NP. It's an exponential algorithm. But occasionally you'll have one of these algorithms where it takes exponential time to solve, so it's not NP, but it is still in NP, because if we are given a solution, a path in this case, we're able to verify that the path meets the criteria in polynomial time. Hard to solve, easy to verify. For example, if someone says, hey, this path here from D to E, A to B to C, da-da-da-da-da, that path, that one is less than 100 miles. I'm just telling you that. Hey, can you check for me? Great. Now all we have to do is follow that one exact path, sum all the distances, and if it's less than 100, great. We solve the algorithm. So this is an algorithm that when given a solution, we can verify that that solution is correct in polynomial time. And whenever we have a verifier that is quick, that runs in polynomial time, that algorithm is in NP. Okay, so we understand P, that's algorithms that can be solved quickly, and NP, algorithms that can be verified quickly. So what's this bit about versus? Why is it P versus NP? Well, that's because there's this very interesting unsolved problem in computer science, which is, hey, are every algorithm that's in NP actually also in P? In other words, if we have a polynomial time verifier for an algorithm, is there also a polynomial time solution for that algorithm? And in practical terms, no. Just like the problem I just presented to you, there's a lot of algorithms, or I should say a lot of problems, where we have polynomial time verifiers, but not polynomial time solvers. And so it seems like P and NP are not the same. However, no one's ever been able to prove that all these problems in NP don't have polynomial time solutions. And so we're all kind of left wondering, well, maybe one day we'll have a breakthrough. We'll be able to solve all of these NP problems in polynomial time. But no one really knows yet. We suspect that they're not the same, because so many people have been working to solve these problems for so long, and we just haven't gotten a solution, but no one's proved it.
Good explanation as well. I like Grok's one, to be fair. NP is basically a superset of P, right? It encompasses, like, P is a subset of NP, and NP encompasses that. So back to this one again. So problems in NP can be verified in polynomial time, but not solved. Oh, gosh. So the traveling salesman problem, verify TSP review, blah, 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 NP complete. Right, we got an hour and a half to smash this out and get done with this part of the course. I'm not gonna lie, it's been a crazy one on the brain, and it's nice going through this and stuff. But I definitely feel this sort of itch to move on to something else now and like build a little bit more. But anyway, traveling salesman problem. A famous example of a problem in MP is the traveling salesman problem, also known as TSP. All right, okay, so that's what all these are. Verified TSP, MP complete. Okay, yeah, cool. The version of the problem that we solve can be stated, given a list of cities, the distances between each pair of cities, and a total distance. Is there a path to all cities that is less than the distance given? So, for example, with the above graph, the problem could be, is the way to travel through A, B, C, and D in less than a distance of 67? The answer would be yes. It would be A to B to D to C. Yeah. Assignment. Our influencers need to travel to conferences to shill their sponsors' products. Since none of them trust Google Maps, they want to put in their proposed routes to locked in, and we will tell them if their route is short enough to be worth their time. Can you say feature group? Complete the TSP function by performing a brute force search using the provided algorithm. The brute force search will unfortunately take factorial time because you'll need to try all possible paths and keep track of the shortest. The provided permutations will give you all possible permutations of a list. For example, permutations 0, 1, 2 returns like that, okay? Pseudocode. So inputs, cities, a list of numbers starting from 0 that each represent a city. Paths, a matrix where each point represents the distance between two cities. So, and then dist, the distance we're trying to beat. Here's the example of the paths matrix, a list of lists. Each list represents the distance from that city to all the other cities. For example, path 0, 1 holds the distance from city 0 to city 1. Path 0, 1 is then also the same as path 1 to 0. So 0, 1 list 0 shows the distance from city 0 to cities 0, 1 and 2. Yeah, obviously for itself it's 0. Makes sense. List 1 shows the distance from city 1 to city 0, 1 and 2. Yep, okay. All the routes and their distances, yep. So its distance between all cities is from city 0 to city 1 to city 2, which is 27. Algorithm. So use permutations function to get the matrix of all possible paths through the given cities, where the first path represents me. Yep. Okay, so possible paths. Possible paths equals self dot permutations, and then we give it the paths. Oh, wait, do we give it the cities? Hold on. Paths is matrix each, but no, so we give it the cities. Okay, iterate over each possible path. So for possible path in possible paths, sum the distances between each city and the path using the path matrix to look up the distances. Okay, sum equals 0, and then we're going to do for So sum of the distances between each city in the path using the paths matrix to look up the distances, so possible path. Sum of the distances between each city in the path using the path matrix to look up the distances. Okay, 0, 1, and 2. Total distance of the path is less than, return true. If no short paths are found, return false. So if was it if the distance sum is less than dist, then return true. So for this part, so the city is going to be like one of these, so it's going to be 0. Yeah, okay, so then possible path is going to be one of these. So then we take so then for distance in paths city, we'll do sum plus equals distance. That not quite. Whoops. Boom, did I nail it the first time? Oh, crap. No, not quite. I passed all the normal tests, though. So what did I get wrong? 5 failed. Read that last bit. So if the total distance of the path is less than the given dist, then return true. Hold on. Sum the distances. So for iterate each possible path permutation. if the so sum the distances between each city in the path using the path matrix to look up the distances. If the total distance of the path is less than look at this print investigation sum from the dist. So for each city in cities, that gives us like the index. Right, so which is just a list of numbers started from, yeah. So iterate over each path, yeah. Sum the distances to each city in the path. So possible path. Sum the distances between each city in the path using path matrix to look up the distances. I mean, what do we need cities for then? Oh, I guess it's just that first bit. So then, so city and possible path. Is that right? Oh, not quite. Okay. So in the possible path for each city, if the top, so some distances between each city, if the each city in the path using the paths matrix to look up the distances. feel like it needs to be that, but I'm trying to think of how do I get that? Ah, so it doesn't quite work. It's something about how I'm indexing into the past, but I'm not quite sure. So don't want to spend too long with this. So let's get moving. So no, there's a rookie mistake. It boots. Can you help? Yeah, it was that. So, common riddle in the world of algorithms. I see you made excellent progress with most of your test passing. However, the last failing test hints at sore misstep in how you calculate some of differences to each possible path. Take a close look at this. Yeah, I know. Remember, the path matrix gives you the distance between two specific cities. For example, path 0, 1 is the distance from city 0 to 1. When you iterate with enumerate, index the position of the possible path list, and city is the city value at that position. How should you use index and city, or rather the city values at consecutive indices, to correctly sum distances between adjacent cities in possible path? For example, possible path is A, B, C. How would you use the paths matrix to get the distance from A to B and then from B to C? No, I didn't think that'd be it. Well, you want the currency, right? So I guess was it like target city? So at this point we've got a list and it'll be like the path. So that's the possible path, yep. And then we loop through possible path, target city. I should use index C, or rather the city values at consecutive indices to correctly sum the distances between adjacencies. And how would you use path matrix to get the distance from A to B and then from B to A, B to C? No. I'm a bit lost. If we explore, it seems we're still grappling with how to properly calculate the total distance for each possible path. So the path matrix is designed to give you the distance from one city to another. So yeah, city A to city B. I just can't quite understand how to get city A, like from. Your current line sum, blah, 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 is trying to find the distance from a city to well itself, which will always be 0. Think of it this way, a path 0, 1, 2 means you go from 0 to 1. Okay, you need some of the distances for each hop in the journey. How do you iterate through possible paths at each step? You can look up the distance between the current city and the next city in the path. Consider starting your loop from the second city in the path and always look back at the previous city. So I guess previous city. Yeah. Need to start the second one. Nearly there. Indeed, you're very close. You correctly identified that you need a previous city, a target city, to look at the distance between the last. However, consider what happens. We index 0 to enumerate in the loop. Index 0, blah, blah, blah. In Python, possibly it will give you the last element list, means your first distance we calculated. In the last city, so which in part of the choice. How can you adjust your loop to start calculating distance only from the second city onwards, ensuring you always have a valid previous city to refer to? Hold on, I need to look at the syntax again. So, for loops. Okay, hot Python enumerate start at 1. Oh, just do that. That work? Not quite. I don't know. I don't know Boots. I don't know how to start at index 1 with enumerate rate. You're so close to quiz you grasp the concept of needed previously, blah blah blah. Does indeed change the starting value of the index. It doesn't quite help us with the pair of cities we need for each segment of the journey. Remember, we want to go from city A to city B, city C. Okay, so instead of enumerate, think of how you might loop through possible path using a standard for loop with a range. Okay, right. If it's just as simple as like doing that, so I guess possible path. It's just going to be, I guess, possible path current. That's going to be the target city, right? Target underscore city. And then previous city is going to be that -1. Range. I guess possible path length, is it? Like, so like we do length, give it this, and then we say start at 1, and then target city, index to that, and then previous city index. Hold on, target city, previous city. So then target underscore city equals possible path. Target city. Target city index. Target city index, and then it's going to be target city index -1. Does this work? Please tell me it works. Oh, come on. How have I not solved this yet? A bit of a tricky range function indeed. You're right on the path to solve this, but range function needs a little adjustment. Oh, start and stop. The loop goes from start up to, but not including. Whoops, I got it in the wrong place. So starting from 1 that way. Ah, crap. Thanks, Boots. Let's see their solution, see how much better it was. So permutations, so the same thing as me. Total distance, yeah. So then that's when we started matching up. So for I in range, total distance is path. Yep, okay. It's just simple as that. Okay, so it's just written more succinctly. Okay, so verified TSP. TSP takes factorial time to solve because we're forced to try every permutation of all possible cities. For example, given 40 cities A, B, C, D, you need to try all this. That's 4 factorial, or 4 times 3 times 2 times 1, 24 permutations. So TSP in MP. Although it takes factorial time to solve TSP, TSP is in MP because we can verify a solution much faster. Let's write a TSP verifier. Complete verified TSP function by implementing the algorithm below. Notice that it runs in polynomial time. Inputs, so paths, a matrix where each point represents a distance between 2 cities. For example, paths, city A, city B holds the distance from city A to city B, and so on and so forth. Distance, the distance we are trying to find a path shorter than, and an actual path, the path we're trying to verify. So get out of the way. So algorithm, loop over each city in the actual path. Okay, so for each city in actual path, sum the distance between each city in the actual path. So I guess actual sum equals 0. Sum the distance between each city in the actual path. Yep, so then previous, it's going to be the same thing again, isn't it? So previous and underscore city. And target, it's got city underscore index. Range of 1 to length of actual path. So target square city equals actual path, and then target city index, and it's going to be actual path target city index -1. Sum the difference between each city and the actual path. So sum plus equals so then if actual sum is less than dist, then return true. Otherwise, return false. So it'll be paths dot I guess previous city to target city. Whoops, not even close. Whoops, actual sum. Hey, let's see that solution. Just as elegant. Even better. Just more succinct. So, TSP review. Consider the TSP algorithm that we wrote, that, and verifying. The big O of TSP is blank, and verified TSP is blank. So, I'm pretty sure this is O of n, and then O of n factorial for that, because it's going through all permutations and stuff. So I think the answer is that. Yay! But can you explain it, please, Boots? Just so we got, So, answer is ON factorial for TSP and ON for verified TSP. Let's break down why. So, big O for TSP is ON factorial. The TSP function generates every possible order in which cities can be visited. If you have n cities, the number of possible routes permutations is n factorial. N factorial, the function checks each one, so the number of operations grows rapidly as n increases. For example, 5. Yep. So it takes the specific path and simply sums the distances for the sequence, loops over it once, and that's it. TSP function is in class Underwater Basket Weaving 101, P and MP, P and MP, P. Well, it's P and MP. Oh, no? Oh, MP. Explain? So, great question. Why is TSP function belongs in the MP complexity class and defined in complexity classes? Problems that can be solved in polynomial time efficiency, problems where solution can be verified in polynomial time, but finding solution may take exponential time. Oh, right, yeah, okay. I forgot that slight difference. Problems that can be solved in polynomial time. Okay. Yes, it can't be solved in time, but it can be verified. MP complete. So some, but not all problems in MP are also MP complete. A problem in MP is also MP complete if every other problem in MP can be reduced to it in polynomial time. What does reduced mean? A problem in MP is also MP complete if every other problem in MP can be reduced to it in polynomial time. What does reduced we have to start thinking in a chat to just like verified accounts and getting all sorts of weird bots going on. Polynomial time, what does reduce mean? We won't deep dive into the subject of reductions in this course, but we'll cover the basic idea. A reducer is an algorithm that transforms some problem A, into a different problem which is already solved. So problem B, then problem A can be solved within the algorithm solving problem B. So problem A, reducer, problem B, solver algorithm, problem B, solution to problem A. Let me read that again. A reducer is an algorithm that transforms some problem, so problem A, into a different problem which is already solved, problem B. Then problem A can be solved with the algorithm for solving problem B. However, the reducer itself needs to be fast. Problem A is reducible to problem B if the reducer can run in polynomial time. So who cares? Well, this means that if we can find an algorithm that solves any of the MP complete problems in polynomial time, then all problems in MP can also be solved in polynomial time. Super duper smart computer scientists have proven it, trust me, or optionally read more about it. So for a problem to be MP complete, all problems in MP must be able to reduce it to, in the quantum realm, in space-time, polynomial time, and exponential time. To MP complete, all problems in MP must be in polynomial time. A problem in NP is also NP complete if every other problem in NP can be reduced to it in polynomial time. What does reduce mean? Okay, I'm not quite sure on that concept, but it's fine. A solver blank, a solver for blank problems can be used with a reducer to solve all problems in blank. So a solver for NP complete problems can be used with a reducer to solve all problems in NP. Not sure I quite understand the concept, but it's fine, we move. 50 minutes to try and smash through these. I don't know if it's gonna work out because I got more code to write. So verifying solutions. So let's circle back to this idea of slow to solve, fast to verify. Even when we aren't specifically talking about P and NP, the concept of slow to solve, fast to verify is very important in real world software. As a trivial example, imagine the password on an email account. When a user inputs password like password for me, it's easy to verify that the password matches the one we have saved on file. It's literally as easy as this. The useful bit is that it takes much longer to guess the correct password. The passwords example demonstrates the guess verify concept well, but when it comes to storing passwords in plain text, this example is very insecure. We'll cover how to handle passwords in production system in a future course. So assignment. The influencers who use locked-in are worried about account security. We've assured them that their passwords are long and strong enough, but they want data. Complete the getNumGuesses function. It takes a password length as input and returns the number of guesses required to ensure that a password of that length or shorter is guessed. Assume a brute force guessing strategy on the part of an attacker. A guesser needs to be able to guess all possible passwords up to and including the given length, for example, like that. So assume that only the 26 lowercase English letters can be used in passwords. Here's some example input output. I guess it's going to be just the length to the power of itself, right? I can't remember how you do exponential in Python again. So how do you do exponents? Nope. Whoopsie. Um. I feel like this is just some like a very, very simple sort of calculation where you basically just take so isn't it just so 1 times 26 is 26 plus 2 to the power of 26. Hold on. So if there's one letter, there's 26 letters, like combination. If there's 2 letters, then there's 2 to the power of 26, right? Then length. Need something with a loop, right? So this would go from index. Yeah. Hold on, calculator. So 2 exponential 26 Oh, it's the other way around. It's 26 to the power of the index, right? Unsolved problem in computer science. It asks whether every problem whose solution could be quickly verified it is in MP can also be solved quickly is in P. The question is, are all MP problems really just P problems? The answer is we don't know, but probably not. Why do we care? All problems in MP, hard ones like traveling salesman problem, have been proven to also be solvable in polynomial time if we can find a solution to just one MP complete problem. If a single MP complete problem can be solved quickly in polynomial time, that means that all problems in NP can be solved in polynomial time. That would be a huge deal, particularly because it would break digital security systems that rely on the difficulty of certain NP problems. So what happens if we find a polynomial time solution to NP complete problems? We learn nothing. MP equals NP, or P is not equal to NP. What happens if we find a polynomial time solution to NP complete problem? We learn nothing. P equals NP, or P is not equal to NP. That one? Explain. So let me break down P equals NP and the correct answer. The key insight lies with understanding what NP complete problems represent in computer science. So what makes NP complete problems special? NP complete problems are the hardest problems in the NP class. They have a unique property. Every problem in NP can be reduced to any NP complete problem in polynomial time. This means if you can solve NP complete problem quickly, you can solve all problems in NP quickly. Why finding polynomial solution proves P equals NP. Here's the logical chain. If we find polynomial time solutions for any NP complete problem, then that problem is in P. Since every NP problem can be reduced to this NP complete problem in polynomial time, we can solve any NP problem by converting it to NP complete problem, solving NP complete problem polynomial time by assumption, converting it back to thing. Therefore, every NP problem in NP can be solved polynomial time, which means every NP problem is actually just a P problem, which proves that. Okay, proves the theory. Does P equals NP? Yes, we don't know yet, but probably not. No, it's impossible to know. We don't know, but probably not. The negative case. So we do not know for sure that P equals NP because we can't find any polynomial time solutions to NP complete problems. Additionally, we have been unable to prove whether P does not equal NP. We suspect P does not equal NP because it's been so difficult to prove that P equals NP. That said, it's actually more complicated to prove the negative case. To prove the positive case that P equals NP, we simply need to solve an NP complete problem like TSP in polynomial time. In order to prove the negative case that P is not equal to NP, we would need to exhaustively prove that there's no possible way to solve TSP in polynomial time. That's a lot trickier. P is not equal to NP is, we don't know, but it's false, right? Yeah, we don't know. Yay! It's simpler to prove P equals NP than P is not equal to NP. NP hard. So all NP complete problems are NP hard, but not all NP hard problems are NP complete. The determining factor between NP complete and NP hard is not all NP hard problems are in NP. Okay, so NP hard, NP complete, NP P is not equal to P. NP hard, P equals NP equals NP complete. All NP complete problems are NP hard. But not all NP hard problems are NP complete. The determining factor between NP complete and NP hard is that not all NP hard problems are NP. Some are P problems. Okay. Definition. A problem is NP hard if every problem in NP can be reduced in. A problem is NP hard if every problem in NP can be reduced into a polynomial time. Compare this to the slightly different definition of NP complete. A problem is NP complete if it is in NP and every other problem in NP can be reduced into it in polynomial time. So a problem is NP hard if every problem in NP can be reduced into it in polynomial time. A problem is NP complete if it is in NP and every other problem in NP can be reduced into polynomial time. Okay, the difference is that NP complete problems must be in NP. or in other words, they must be verifiable in polynomial time. NP-hard has no such restriction. NP-hard problems must blank in polynomial time. NP-hard problems must have reductions from all NP problems, be web scalable, be verifiable, be solvable. Must have reductions from all NP problems. All blank problems are also all NP complete problems are NP hard. Yes. Okay. How many lessons? 1, 2, 3, 4, 5. 5 lessons. I think we can maybe do this. Maybe. A half an hour or so. So, prime factorization. So let's solve a commonly misunderstood problem in computer science, finding the prime factors of a number. Almost all modern cryptography, including a browser's HTTPS encryption, is based on the fact that prime factorization is slow. For now, let's focus on the speed of factorization and how it relates to P and NP. Finding a number's prime factors is an NP algorithm. When given two prime numbers and their product, all we need to do is some simple multiplication to verify correctness polynomial time. Given a number, finding its prime factors is a much more difficult problem. Exponential time is the best we know of. The trouble is not that no one has formally proven that there is not a polynomial time algorithm for finding prime factors. So we're technically unsure if the problem is P or if it's NP complete. Either way, let's build it. The algorithm. So given a large number, return a list of all the prime factors. So like that. So divide n by 2 as many times as you can evenly, no remainder. For each division, append a 2 to the list of prime factors. So I guess prime factors let's call list equals that. For each division, append a 2 to the list of prime factors. Okay, so I guess while n divided by 2, the modulo thing, isn't it? So modulo okay, so prime factors list dot append 2. By now, the n must be odd. Start a loop that iterates over all odd numbers from 3 to the square root of n inclusive. What the heck? By now, n must be odd, so we'll just do print. Not m, n. Oh, yikes, whoops. And then I guess return prime factors list. Okay, so it's not mutating as we go along, so we need to do something about that. Okay, that worked better. Okay, so that's working that part. So then, pretty confident in that now. So then, by now n must be odd. So I guess like print n and yep, okay, that's right. So by this point, it should be odd. Start a loop that iterates over all odd numbers from 3 to the square root of n inclusive. Use math.square root. So for each number I in, I guess, range from 3 to math dot square root of n. So for each number I, if n can be divided evenly by I, then divide n by I and append. Okay, so if n modulo I is equal to 0, evenly by I, then divide n by I and append I to the list. So n divided by I and divide n by I and append I to the list. For each number in I, if n can be divided evenly by I, then divide n by I and append I to the list. Right, and then append I to the list. So then append I. Repeat this nested loop until I can't divide evenly into n, then move on to the next I. A Python turn floats into int. Just use the int function. Okay. If n is still greater than 2 after... Right, okay. Repeat this nested loop. Okay. Then if n is still greater than 2 after that loop, it must still be a prime, so just append it to the list. So I guess then if n is greater than 2, then prime factors score list dot append n. Oh, crap, so close. I'm not sure where it's breaking down though. Actual 49, expecting 7 and 7. I almost had it boots. Oops. Okay, you certainly on the right track, young bear. I can see you've made good progress with the prime factors function. I can see a couple of things in your code, the output that we can explore together to get you past these challenges. First, take a look at the warning in the lesson about the type of numbers in the return list. You have some output like, oh, have I? You have some output like 7, 11, blah, blah, blah. How might you ensure that all numbers you append to prime factors list remain integers, especially when you're performing division? Int. Okay. Secondly, let's re-examine the loop where you divide by odd numbers. The algorithm specifies to iterate from 3 to the square root of n inclusive. Consider your range function call. Well, how does this range function work with the upper bound? Does it include the n value or stop just before it? Yeah, okay. So that's the kicker. Okay. It was an index issue. Okay, but I pretty much got it. I'm happy with that. So prime factoring review. Consider the code from the last assignment. It was a lot simpler. Which is this problem definitely a part of? P, MP hard, or MP complete, or MP? MP complete. Oh crap, MP hard. No. Oh no. Oh, I think it's because we can verify it, right? So it's not MP complete, it's not MP hard for that reason. It's not polynomial time either. Okay, so which is this problem definitely a part of? So MP hard, MP complete, MP. Correct answer is MP. Let's break it down. The code in the lesson is about finding prime factorization of a number. The underlying computation or problem is, given a number n, find its prime factors. We talk about P and NP and the like. We're referencing complexity classes in computer science that describe how hard the problems are to solve with respect to time, resources, computers. So what does NP mean? So NP stands for non-deterministic polynomial time. It includes all decision problems, yes, no, for which any given solution can be verified quickly in polynomial time. So we can, yeah. So why is prime factorization NP? If someone gives you a set of numbers and say, these are prime factors of n, you can multiply them all together and check if their product equals n in polynomial time, verifying the factorization is quick. Therefore, prime factorization is NP. Why not the other ones? So P, problems can both be solved and checked quickly. We currently don't know efficient algorithm for factoring very large numbers. NP complete, these are the hardest problems in NP. If you could solve one NP complete problem quickly, you could solve all of them quickly. There's no reason to believe prime factorization fits in this category. It hasn't been proven. NP hard, these are problems at least as hard as any NP. Prime factorization is not even known to be hard in this technical case, just that we can definitely check factorization quickly. In short, prime factorization is definitely NP, but necessarily P, NP, or NP hard. Nah, it's alright, no more quizzes. Prime factoring review. Given two large primes and a product, can we verify that two primes multiply into the product polynomial time? Yes, we can. Prime factoring review. Okay, and then we've got a subset sum problem. Okay, big O analysis. Let's denote n as the integer input and s as the size of n in bits. Let's denote n as an integer input and s as the size of n in bits. So s equals log 2n. Notice that our first loop iterates log n times and the second loop iterates square root n times. With the big O with respect to n is O square root n. That's fast. That's polynomial complexity, which would lead us to believe the problem is in P. Wait, the problem is that by definition, when computer scientists talk about this problem, they are talking about the length of n in bits. What we will call s, for example, the integer 255 only takes 8 bits. Yeah. So 241 is that in binary, since s is log 2n, a complexity of O square root n is equivalent to O square root of 2 to the power of s. The complexity in respect to the number of bits is exponential. What is that algorithm's big O complexity when n is the input integer and s is the size of the input in bits respectively? Subset problem. Oh, can this be the last one tonight? Can we finish this? Can we make this the winner night? Gotta push through and do it. Okay, so see how's everybody doing out there? You having a good time? Laughing much? This is quite hilarious to watch, I imagine, for people who are more experienced at this part. So subset sum problem. So in locked in, we have a list of influences and their respective follower counts. We want to find a subset of influences whose total follower count is equal to a target number. This problem is known as the subset sum problem, which is an NP hard problem. It asks the question, can we pick numbers from a list to add up to a target number? Can we pick numbers from a list to add up to a target number? Assignment. Complete the subset sum function. It should take a list of integers, nums, and an integer target, and return true if there exists a subset of nums that adds up to target, and false otherwise. We'll use a recursive brute force approach to solve the problem. Brute force just means we'll try every possible combination to see if any of them adds up to the target. It's a pseudocode. So subset sum. So nums is a list of integers representing the follower counts of influences. Target, the target sum we want to find a subset for. Output true if there exists a subset of nums that adds up to target, otherwise false. So I guess we'll do just return false by default, and then here true if it's so sum equals 0, and then I guess so I guess if whoa, what the hell's going on there? So if subset sum of nums if there exists a subset of nums that adds up to target, so if it's turn true, call the helper function starting with the last index in nums and return its result. So the algorithm for this one is, so algorithm call the helper function starting with the last index in nums. Oh, right, I see, right. Okay, so for num in nums, Python loop backwards. Okay, so then I think that's right. So pseudocode for find subset num. So nums is a list of integers representing all kinds of target some blah blah blah. So output true if there exists a subset of nums that adds up to target, false otherwise. So if the target is 0, then return true. So if target is equal to 0, then return true. If the index is less than 0 and target, so then if index is less than 0 and target is not equal to 0, then return false. If the number at the current index is greater than the target, call the helper function with the same target with the index generated by. So if the current index, so if the nums current index is greater than target, then call the helper function with the same target with the incorrect. With the same target and an index decremented by 1. Okay, so nums target with the same target and index -1 and save the result. Result equals that. Also call the helper function with the target reduced by the value of the current. If either of these calls return true, okay. Index greater than target equals false. And then also call the help function with the target reduced by the value of the current. Also call the function with the call the helper function with the target reduced by the value of the current element and the index decremented by 1. So second helper equals false. So then second helper equals this. Find something, and then also call so with the target reduced by the value of the current element. The extra target reduced by the value of the current element. Minus nums index. If either of these calls, so I guess if index greater than target, if either of these calls return true, if or second helper return true, otherwise return false. List index out of range. So if the number of the current index is greater than the target index, just print debug nums index. One, two, three, 4, 5, 6, yeah. Plenty failed. Target 60x. Print this. This is never returning true for both of these. Hold on. Let me have a look at it. Come on. It's late. Boots. Help me out here. Okay, I can see your code and your test output. Let's look at the mischievous bug together. I won't give the solution directly, but I'll nudge you with questions. So in your subset sum function, use a for loop over indexes, only check length -1 down to 1, not including 0. Oh, is that why? Why do you think the loop executes index 0? Should we consider all possible starting points including 0? Yeah, that's a fair point. In your helper, nums index greater than 0 is true. You only make one recursive call. But even if it's not greater, you might still want to consider both possibilities, including or not including the current element. Think if the current number is not greater than the target, shouldn't you also try the branch that skips it? Your helper function returns true or false, but in your loop, in subset sum, you compare the result of target. Is that the right comparison? Oh. Oh, wow. That was it. That was all was needed to fix it. Those 2 bits. Wowee. What a night. We did it, chat. We're here. Claim 11,000 XP. I'll take it. Blimey. That just shoved me up a whole load of ranks. Read all these. So this is a great introduction. It covers everything. It covers everything with good explanations. But sometimes the the practical work is worded. Practical work could be worded slightly better. So, like for example, when you need to use other self references in a class, or using other variables defined, maybe mention that I was trying to figure out problems, not realizing I needed to use something else from the class. Boots was a life saver in this one, as I'm not very experienced with writing algorithms. I hate spelling rhythms. Rhythms. Yeah. Challenging, but rewarding, and it's hard to make complex topics like this simpler. Race course, definitely a 5-star. It's great. I'll skip the review thing just because there's a lot to say on it and stuff. I'm not quite sure. So let's open the chests. Yay! Yay! Shoot sharp, shoot spree. I'll load the chest open. Oh, I got shot super reward. Gems and salmon and more gems. Yay! Gems and more salmon and gems and an XP potion. Achievement unlocked. Sharpshooter mastered. Complete 21 sharpshooter sprees. 5.25% of students have heard this achievement. I'm up there then, my friend. So we get to the end. I've already done that, so like close. Back to the dashboard. What have I got here? Beautiful, beautiful, what we say. Beautiful. So I guess I'll die. I'm in the Dark Vampire League. The hell is that? Let's share on X. The right one. That's today, yep. This one. Here we go. Let's post it on locked in or lonked in. Okay, we got that. So add to LinkedIn. This was Python. Data structures. Algorithms. I guess save. Have to add the image. Can't remember. So we go save. Yay! And then go next. Not. So then the instructions say not that. Oh yeah, there we go. Let's find lane on here. Wags lane. Wags lane. Okay. Here we go. So those two are done. Pretty sure I'm happy with that. Can close. And that'll do. Yeehaw. So that's it for tonight. We can brush off. I'm going to take a break. I'm going to take a break tomorrow. Tomorrow night. I'm not going to be on streaming. I'm going to take a break, and I think what we'll do is we'll start Learn Memory C Management Wednesday, Thursday this week. Don't know what's going to. I'm skipping past the AI agent Python thing because I think that was added in as I was going. That's why there's like a gap there. I think there's some optional things that were added for the Python book, the bookbot one as well. So we'll come back to that and finish that at some point, but I want to kind of carry on the original track we were going on. So how many are we down? So we're down 10, and there's 23. Now the thing is, like, a lot of these early ones, although not as kind of complicated, I guess some of them not as complicated anyway, took a lot longer because like there's like more lessons involved and stuff. I think this is another big one, this is a big one, but then a lot of the other ones like are much smaller. At least they look at CI/CD, Docker, like I think we'll get through them a bit quicker, but I guess we'll see, pun intended, when we do the next one in Learn Memory Management for C. So that is the one. 24 hours of content. So hey, TJ DeVries. So that's the man. He's the myth, the legend. He is the one leading this. So it's 24 hours of content. So I'm just thinking if I'm doing 3 hours a night. Oh, I've got no calculator head now. So like, how? 24 hours. So 24 divided by 3. Whoops. divided by 3. 8 sessions, so 2 weeks. Probably take longer than that, depending on how how much I struggle through it. But it could be fun. I think we'll start it, but then we'll come back to it. Oh boy. So there's 11 chapters in this. And I think each one's going to be probably like a hefty go. But we're there. That'll be doing it. We'll be doing that. Whoop, not that one. Go back. No. We want C management. So we're coming back to here, and we'll be getting going. And yeah. So that's going to be it for tonight. All done. If you've been watching and enjoy it, thanks for coming down. Hope you had fun. Hope you learned something from it. Sign up for Boot.dev is the thing that you're after. If you're coming in from the future, thanks for traveling back. Let us know where you get the time machine from. And that big... Oh, it's just a cough. And yeah, thanks very much. I'll see you next time. Probably on Wednesday or Thursday. Peace. And sayonara.